In this video, we're going to examine the structures of disaccharides and polysaccharides, which contain multiple monosaccharide units linked together, usually via at least one of the anomeric carbons in one of the sugar units. Disaccharides in particular include two sugar units, as suggested by the name. And the bond, the CO linkage that actually links the two sugar units together is known as the glycosidic bond. And this tends to be a very special bond, as that CO bond can often be broken under hydrolytic conditions, for example, inside an enzyme or under strongly acidic conditions most commonly. And so the anomeric carbon of one sugar is typically involved, and a hydroxyl oxygen on the other sugar unit, which may or may not be the anomeric hydroxyl on the other sugar unit, is typically involved. So here we're going to look at a couple of examples of the most important disaccharides. And the first here is maltose. Maltose is obtained from the hydrolysis of starch, and it's a disaccharide containing two glucose units. Maltose is a reducing sugar, and it undergoes mutarotation. And both of these are due to the fact that maltose has a hemiacetal within its structure. Pause the video and see if you can spot the hemiacetal in this structure of maltose. Did you find it? It's at this carbon 1 that's not part of the glycosidic bond. Notice that in this glucose unit on the left, the glycosidic bond involves carbon 1 in that glucose unit, and the hydroxyl group linked to carbon 4 in the other glucose unit. We're going to come back to that in a second. This means that carbon 1 in that glucose on the right is free, quote unquote, as a hemiacetal. This means it can open, and that open acetal, which is now an aldehyde, right, hydroxyaldehyde, can reclose to form the beta anomer. That's where mutarotation comes into play, and that aldehyde group, which has now been revealed, can be oxidized, and this is what makes maltose a reducing sugar. Now let's take a step back and dig into the glycosidic bond in this structure in a little more detail. So we noted that the glycosidic bond here is this bond in purple between the anomeric carbon of one glucose unit and an oxygen linked to carbon 4 of the other glucose unit. Because these carbons are involved, these two carbons are linked to this sort of common oxygen atom in the glycosidic linkage, the linkage is called a 1,4 linkage. Carbon 1 in one unit and carbon 4 in the other unit are involved. Now, what about the alpha? Well, the alpha refers to the configuration of the anomeric carbon involved in the glycosidic bond, which is this carbon 1 right here. With this oxygen in an axial position, and with this being a D sugar, this corresponds to the alpha anomer of this glucose unit on the left. And again, this is worth pausing and verifying if alpha and beta are a little bit new to you. But this is the alpha configuration of that sugar, and so the alpha prefix here indicates that the glycosidic linkage is between an alpha positioned oxygen at carbon 1 of the left-hand glucose unit. When two anomeric carbons are involved, you'll sometimes see two alpha-beta designators here, although most commonly only one anomeric carbon is involved, and so we only need one alpha or beta in naming the glycosidic linkage. So overall, this entire linkage is an alpha 1,4 glycosidic bond. Cellobiose is a related disaccharide that contains not alpha 1,4 linkages, but beta 1,4 linkages. So notice if we number the carbons in cellobiose, we still have a linkage between carbon 1 and an oxygen linked to carbon 4 in the right-hand glucose unit. And aside from that, we've got two glucose units, just as in maltose. The key difference between maltose and cellobiose is in the configuration right here. Notice that now we have an axial H and an equatorial oxygen where we had an axial oxygen in the maltose. So the glycosidic bond now is not an alpha 1,4 linkage, but a beta 1,4 linkage in cellobiose. This slide highlights disaccharides involving two different monosaccharide units, lactose and sucrose. Lactose is a beta 1,4 disaccharide that contains galactose and glucose units. And in our structure here, we've got the galactose unit on the left, this axial hydroxyl group at carbon 4 right here is a dead giveaway that this is galactose. And notice that the hydroxyl group here involved in the glycosidic linkage and at carbon 4 is in an equatorial position, indicating that this is a glucose monomer. The glycosidic linkage in lactose is a beta 1,4 linkage. We've got carbon 1 involved in the glycosidic bond and an oxygen linked to carbon 4 involved in the glycosidic bond. And notice the configuration here is the beta configuration, and so it's a beta 1,4 linkage. In sucrose, we've got an interesting situation where we have glucose and fructose units involved. The glucose unit on the left here is in its pyranose form, 6-membered ring. The fructose unit on the right in this structure is in its furanose form. Another important thing to notice about sucrose is that it does not exhibit mutarotation and it is a non-reducing sugar. The reason for this is straightforward if we take a look at the anomeric carbons in both monosaccharide units. The anomeric carbon in the glucose unit is involved in an acetal, the glycosidic bond. But the anomeric carbon in fructose is also involved in the glycosidic bond. There is no free hemiacetal in the structure of sucrose. This is worth pausing and poring over the structure to verify this. There is no hemiacetal in the structure of sucrose. So it can't open to form an aldehyde, that's why it's non-reducing, and there's no way to invert the configuration, for example, at either of the anomeric carbons without breaking the disaccharide apart completely. So it's not going to exhibit mutarotation either. As their name suggests, polysaccharides are polymers of monosaccharide units linked by glycosidic bonds. And we can typically think of polysaccharides forming via repeated glycosidation at carbon 1 on the growing polysaccharide chain. So the last sugar on the end of the chain has a free hemiacetal that can participate in a glycosidation reaction to add one more monomer on the end of the chain. We'll see what that looks like here in a second. And they're seen in living systems for a variety of purposes. For example, structural rigidity, chitin, and cellulose are important examples of polysaccharides used for that purpose. Energy storage, we can think about glycogen and starches there, as well as cell signaling. Cellulose is a polymer of beta glucose with beta 1,4 glycosidic bonds in its structure, and those are highlighted here with the carbon 1, the anomeric carbon, highlighted in blue, and that hydroxyl group at carbon 4 that is the nucleophile in forming the glycosidic bond highlighted in red. And so we can think of this as a beta 1,4 polymer of glucopyranoses. That's cellulose. How does cellulose form? Well, this is worth thinking about because this is going to give us a general model for thinking about the mechanism of polymerization of sugars in general. That carbon highlighted in blue, the anomeric carbon, is an electrophilic carbon. And we can see that if we imagine this occurring under acidic conditions, we can protonate the anomeric hydroxyl and then kick it off as a leaving group and a beta elimination step, and we get an oxygen-stabilized carbocation at carbon 1 at the anomeric carbon. At this point, another sugar molecule can come in, and the hydroxyl group at carbon 4 of that new sugar molecule attacks the electrophilic, or forms a bond to the electrophilic anomeric carbon in our growing polymer chain, and this creates a new glycosidic bond. And the cycle repeats, so on and so on and so forth. And so often in living systems, this will happen in the active site of the enzyme, So the enzyme can steer this hydroxyl group at carbon 4 to bond selectively to the anomeric carbon. If you just took, for example, glucose and tried to achieve this without any sort of templating or selective catalyst in like a laboratory reaction flask, it's not going to work very well because all of these hydroxyl groups are nucleophilic in their own right. But in the active site of an enzyme, which can steer the C4 hydroxyl group right towards that electrophilic anomeric carbon, this can happen with high fidelity, very selectively. Amylose is actually quite similar to cellulose, but consists of alpha 1,4 glycosidic bonds rather than beta. So it's a polymer of alpha glucopyranose, and here I'm highlighting the alpha CO bonds to each anomeric carbon in the glucose units. So amylose is an example of a starch, and starches are primarily used for energy storage, right? Organisms can hydrolyze off these glucose units chew those up in glycolysis and get energy out of that glucose skeleton, essentially. But as a polymer, in polymer form, this is relatively stable and so can hang around and organisms can use it for energy storage. Now, amylopectin is similar to amylose in that it consists of alpha 1,4 glycosidic bonds, but amylopectin also includes branching points. So every few sugar units, there is a 1,6 linkage, alpha 1,6 linkage that creates a branch. So amylopectin is more highly branched, and this leads to some differences in properties and capacity for storing energy and that kind of thing.